Let's take our first look into chapter 16 and talk about radioactivity. Now, since this is a course on safety and kind of public health and regulation, it makes the most sense to talk about who is in charge of regulation for radioactive materials. And it comes down to a few groups. First, we have the NRC, the United States Nuclear Regulatory Commission. Their primary job is to look at nuclear power from a civilian standpoint and to monitor the nation's nuclear power plants. That's what their job is. This kind of goes hand in hand, but is largely separate from what the Department of Energy is looking at. Now, the Department of Energy is also interested in nuclear power and radioactivity, but they're looking at it from a couple of other perspectives. First of all, they want to look at research. Are there ways that we haven't thought of yet to use nuclear material? When we're done with nuclear material, is there a way to use the spent nuclear fuel? Are there other reactors that we could possibly make that would work to take the byproducts of nuclear reactions and use them for our own purposes, better purposes? They also oversee all the construction and operation for our waste disposal sites. They also certify the packaging for radioactive material transportation. So their job deals a lot with kind of dealing with nuclear waste, trying to find new and innovative ways to use nuclear fuel, and making sure that nuclear materials are transported safely. That's the Department of Energy, that's their job. So when you think about nuclear power, these two agencies are probably the two agencies that come to your mind the quickest, the most often, if you've ever even thought, stop and wonder about nuclear power in the first place. And for the most part, these are the agencies that matter. But there are a couple of other agencies that maybe weren't on your first idea, maybe weren't on your short list, that do have some important things to consider as well. So for example, the EPA. The EPA establishes exposure limits to radiation. Primary purpose there is to protect our own public health. So they set values that say, okay, this is how much radiation you can be exposed to in a given day, in a given week, in a given year, and still maintain a normal quality of life. OSHA, well, they do kind of the same thing. Only they're concerned with what you are exposed to at the workplace as opposed to getting to and from work, sitting at home, that kind of thing. And the Department of Transportation, again, they deal primarily with how do we transport this stuff. So while the DOE, while the Department of Energy approves all of the materials that will be used in shipping, the Department of Transportation is actually responsible for the enforcement and for creating procedures to help eliminate or minimize risk. So those are the government entities that are in place that deal specifically with different aspects of radioactivity and our use of radioactivity in different functions. To finish off today's introduction, we're just going to go over and review a couple of concepts that we learned earlier in this course. Dealing again with the nucleus. So I believe it was chapter 2, maybe chapter 3, where we got into kind of what the nucleus is made up of, what an atom looks like. We talked about protons and electrons and neutrons. Well, in nuclear chemistry, we are focused primarily on the nucleus. Don't care about the electrons. The electrons participate in normal chemical reactions. We just spent the last 2 chapters talking about what those electrons do. This chapter, we don't care about the electrons because the electrons have nothing to do with nuclear processes. Nuclear processes are all about that nucleus. And inside of that nucleus, we know we have protons and we have neutrons. And we can talk about those protons and neutrons based upon a couple of different numbers. Remember, we talked about the atomic number, which described the number of protons. And then we talked about the mass number, which described both. And so we established at that time that what makes an atom, what makes gold, gold, what makes carbon, carbon, is the number of protons in its nucleus. That's what the atomic number is all about. But we also established at the time that there are differences in the nuclei of a given sample of carbon, for example. There are differences in the nuclei in a sample of iron, for example. And those differences in those different atomic forms of the same element had to do with the neutrons and had to do with the mass number. And so when we identified isotopes of a given element, we would always identify an isotope by 2 things: the element's name itself and its mass number. So we could do things like talk about carbon 12, which you would understand that carbon is the identification of the element, and 12 would be its mass number. And from that designation, we could look at the periodic table and say, okay, carbon 12, carbon has 6 protons. And if its mass number is 12, 12 minus 6 means that it has 6 neutrons as well. I can contrast that with carbon 13, which have the same protons, 6, but 7 neutrons instead. And so we looked at these 2 concepts very closely in chapter 2 as a way of kind of building what an atom looks like and how we can tell the differences between one atom and another, and one isotope of a given element and a different isotope of the same element, because there are distinctions. I can have carbon 13 and nitrogen 13. Both have the same mass number, but they have different number of protons, and that's what makes them different. So if I look at carbon 12 versus carbon 13, they're both carbon. They both have 6 protons in the nucleus. They both have very similar chemical and physical properties. They have slightly different nuclear properties. And that's what we're going to get into, the difference here in this particular chapter. And so the last thing that we will mention today has to do with those isotopes and the fact that every nucleus, every particular element has at least 3 isotopes, 3 different nuclear forms of the same element. Some of those nuclei are stable. The ones that are stable are the ones that we would have talked about last chapter, that go through normal chemical reactions and make molecules. Others are not stable. The ones that are stable, we refer, or excuse me, the ones that are unstable, we refer to as radioactive. Radioactive substances will undergo transformation spontaneously. 1 minute it's carbon, the next it's nitrogen. Why it does that is because of this instability inside of its nucleus. And we can rate the instability based on something that's called half-life. Half-life is the amount of time it takes for half of a radioactive sample to change to something else. The faster that half-life is, the more unstable it is. The slower it is, the more stable it is. So take, for example, carbon-14. Carbon-14 is not the stable form of carbon. It is radioactive. Its half-life is just this side of 5,700 years. So it sticks around for a little bit. Meaning it can undergo normal chemical reactions because it's not going to decay very quickly. So does it undergo chemical change? Absolutely. Does it undergo nuclear change? It can, but it does so slowly. And so we'll talk a little bit more about half-life and get into the actual spontaneity, what it breaks down into, starting with next lecture. Have a great day.